Okay, well, welcome to week 2. For those of you who weren't here last week, welcome to the main program. And for those of you who were, welcome back. We're now much sort of less sort of intensive than we were last week. So we've got sort of time for more elongated seminars, more discussion after the seminar. So we've got plenty of time. So week 2 is broadly based around the theme of change points and related processes in social and economic sciences. So we're going to have talks on sort of everything from social networks through to econometric and financial applications this week. But our first speaker is going to be Hao Chen from UC Davis, and she's going to be talking about graph-based change point detection.
So first of all, I would like to thank the organizers for organizing such a wonderful workshop, and I learned a lot in the past week. And it's my great pleasure to talk about my work in change point detection for a sequence of multivariate observations or even more complex observations. And to summarize, the method is based on a graph that is constructed on the observations. So that's the graph-based comes from. So this graph does not mean that the original observation is a graph. It means that the method is based on a graph that constructs on observations. And it's a joint work with my PhD advisor, Nancy Zhang. But she left to another university during my PhD. So unfortunately, I was adopted by David Sigmund, and he taught me a lot in terms of completing this work and some foreign work, and we are still working on. So I would like to express my special thanks to David, and sorry that you have to hear this talk one more time. So to back to the topic, so everyone here knows what a change point is. So in this illustration plot, observations before this time follow one distribution, and observation after this time follow another distribution, and this is the change point. So this is a very easy example, and it's very clear where the change point is. And here the observation is scalar, that at each time the observation is just a single value. And there is a huge literature for change point detection models for scalar observations, both that the observations are independent over time or they have autocorrelation structures. While if the observations are multivariate, that is, for each time the observation is a vector, then the number of studies decrease dramatically as the dimension of the observation increase. And we know that nowadays many data come with the multivariate form, or that we observe a sequence of observation that each observation is non-Euclidean, for example, a network. And the study is quite limited in that area. But there are indeed many examples in that area. And to be more concrete, here are 2 examples I think is quite interesting. So this is one example. This book is called Tranquil Blank, and it is a chivalry novel written in Catalan and published in the 15th century. And this book is considered to be a major influence for a well-known novel, Don Quixote. And so I guess you all know this book. And in this book, in a similar sense about burning books, the priest referred to this book, Tranquil Blank, to be the best book of its kind in the world. So that is well accepted to be the preference of the author of Don Quixote, I think called Cervantes. And also Cervantes indirectly acknowledges the influence of this book by referring Catalan to be the sweetest language, although after Portuguese. So, and also some people consider this book, Tranquil Blank, to be the first modern novel in Europe. So it seems that this book is quite important. But interesting about this book is that, so in the first edition of this book, there are conflicting information about the authorship of the book. And here they are. In the dedicated letter at the beginning of the book, it said that this book was all finished by a knight called Not Martorial. However, in the colorful at the end of the book, it said that Montreal died before he finished this book. And the last quarter of the book was finished by another knight called Martin John de Gabor. And a little bit more history of the book was that the main part of the book was finished in 1460s, while this book was not published until 1490. And this person, Montreal, died in 1498, which was way earlier than the book was published. And Gabor died in 1490, the same year as the book was published. And ever since the book was published, there was like an intense debating about whether this book was finished by only one author or there is a change of author midway. And over years, experts split into two groups, one favoring the single authorship hypothesis and the other favoring a change of author. And nowadays, the majority think that the book was finished by only one author, but still there are majority of people think that there is a change of author. And if we check the Wikipedia page of this book, only I checked it yesterday, so only this person was listed as the author of the book. But if we check the wiki page of this guy or this guy, on both pages, Gabor was listed as to be the second author of this book. So we see that there is like splitting opinion of the authorship of this book. Of course, it's impossible for us to know what's the truth of the authorship of this book unless we travel back to the time the book was written. But we can test whether there is a change of author objectively by test whether there is a change in the writing style of the book. Because different people have different writing styles. Even if one tries very hard to mimic the other, it's still very hard to hide. So in this problem, in total it has 487 chapters. So we can test whether there is a change, there is an abrupt change in the writing style along the chapters. And here, so the index will be the chapter, and each observation is a vector of word counts characterizing the writing style of that chapter. And so for the detail of this, I will talk about more when I come back to this problem later. And here is another example. This is data collected by the MIT Media Lab. They conduct a study involving 90 subjects, and they give them pre-installed, they give them cell phones with pre-installed software, which can record all the phone call logs. And these 90 subjects are students or faculty from one research institute. And the study lasted for almost 1 year, from July 2004 till June 2005. So with this data set, people will be interested in that whether there is a phone call pattern change among these people around this period. This is one way to study whether there is a change of the friendship among these people. And for this problem, we can approach it in the following way, that for each day, we can construct a phone call network with the nodes being these subjects and a link between two nodes if they made a phone call on that day. And this is an illustration plot of such kind of network, that the nodes are the subjects, and if they made a phone call on that day, there will be a link. And there are in total 330 days during that period, so we can construct 330 such phone call networks for each date. And then we would like to test whether there is a change in the distribution of the network along the time. So here, the time will be the date and each observation in a network. And here are only 2 examples, and we know that there are many applications that we have a sequence of observations of complex data, either to be a vector or a network or image that we would like to know whether there is a change at some time. And the change point model would be very useful in these cases. And there are some work having done for the change point detection of a sequence of multivariate observations. And here are some lists. So of course, this list is not exhaustive. And if you know any work that you think should be on this list, you just let me know. And up to my knowledge, most of the work are based on parametric models. And I feel most of them are highly context-specific. That means that they have some assumptions on the distribution of the vector. So for example, these two work, the first two work, they assume that each observation follows multivariate Gaussian distribution with identity covariance matrix. So that's a very strong assumption. And for these two work, they also assume that each observation follows a multivariate Gaussian distribution, but they don't impose any assumption on the covariance matrix. So in order for these two methods to work, we require the number of observations to be larger than the number of dimensions so that we can estimate the covariance matrix. And the last one assumes that each observation follows multinomial distribution. So of course, this is not exhaustive, but so in general, for parametric method for change point problem, they need to have, in order for them to be applicable for high dimension, they need to impose strong assumptions on the data so that so to reduce the number of parameters it need to be estimated. And of course, if the data do satisfy the assumption, then usually this method will be preferred. But many times these assumptions are too stringent for the data. And there are some other methods that are non-parametric or semi-parametric. These two, they are based on kernels, and this one based on the marginal rank statistic. And I feel like this cannot be generalized well to high dimension. And to my knowledge, none of the existing non-parametric methods can generalize well to high dimension. So we see like there is a big gap between what we want to do and what we already have. So our goal here is to develop a general method that can be used to detect change point for a sequence of multivariate observation or more complex observations. And here is the outline. I will first talk about proposed method, and it is a scan type method. And I will then talk about how to control the false positive analytically. And then I will talk about how the method works on these two applications. And if there's still time, I will talk about some power analysis. So first is the formulation of the problem. So we work under the assumption that we have a sequence of independent observations, y1 till yn. And the norm is that there is no, all observations follows the same distribution. And the alternative is that there is a change point tau that observations before tau follow one distribution and observations after tau follow another distribution. So here there are two things I need to point out. So one is the independent assumption. So we know that in many cases that the series there can be autocorrelation along the observations. But we need to first solve the problem of independent case. And then we then think about how to generalize. And also here we look at the offline case that we observe all the observations before we do the testing. And the online version will be some other extension. And here, this alternative of one change point is the most simple alternative. There can be a change the interval that observations within some time interval for one observation for one distribution, observation outside interval for another one. And the change the interval alternative, our method our method for the change interval is very similar to the change the one change point case, but just technically more difficult. And for multiple change points, we can apply the change the interval recursively. So in this talk, I would just focus on the single change point alternative. And our method is non-parametric. So although I use F1, FDR and F1 to denote the distributions, they're actually generic. That is, they do not need to belong to any parametric family. And also, we do not specify what type of changes. So the change can be a mean change, or a variance change, or a combination of some other type. And what we require is that we need an informative similarity measure on the sample space. So essentially, I feel that our method is to convert the change point problem to the the problem of finding the change point to the problem of finding informative similarity measure. And I feel this problem is more achievable because many times there are natural ways to define the similarity measure on the sample space. Even not, I feel it's easier than the change point detection problem. And our method is a scan type statistic, and it's based on a major component, which I call the graph-based two-sample test, and which I will talk more later in the next few slides. So this is a toy example to show how the method works. Here, the data is in two dimensions. It's just so that we can visualize the data very easily. And data is put in this box. And first we observe this one, and then we observe the next one. We observe the data sequentially. And the first 25 observations are from one distribution, and they are denoted by the circles. And then time 25 is a change point. And after that time, observations are from a different distribution, and they're denoted by these pluses. So this is the data we generate. And because we generate data, so we know that which distribution the data comes from. But in reality, we will not know which distribution each data comes from. So we would observe something like this. But we do know the order of the observation we observe because we observe them sequentially. So we know this information. And a typical way of change point detection is that for each time it divides the observations into two groups. One group with observations that observed before this time, and the other group after this time. And then we test whether these two groups are from the same distribution. And we do this test for every single time. And if there's nothing significant, then we see that there's no change point. So that's the most typical way of testing whether there is a change point. And in this example, observation is two dimensions. So there are many ways of forming such kind of like two-sample test. But our goal is like for higher dimension or even more complex data. So actually the choice of such two-sample test is quite limited. And we feel that one work done by Friedman and Rafsky in 1979, that one was quite good for that complex case. So what they do is that they generalize the word runs test, that is for the test for a univariate case, for the two-sample test for the univariate case, and they generalize that to a multivariate case. And what they do is that they construct a minimal spanning tree. So a minimal spanning tree is just a spanning tree that minimizes the total length. And the rationale of their two-sample test is as follows. So if these two groups are from different distributions, so we can think that in the sample space, these two groups are from in different places. And if a minimal spanning tree is constructed, and if they are different, then we will expect the number of links connecting these two groups will be small. And that's the idea of their test. And we found this to be very useful here that, so although when they propose the two-sample test, they will propose for multivariate case, we find it's easy to adapt to the complex data type because, for example, if we think about network, we can think about the space of network. And if we have some way to define which networks are closer or which networks are further, and then we can think of the space of network, and we can still use this method. We construct the minimal spanning tree on the networks. So now each node of the minimal spanning tree would be a network. And then we use the same rationale. So we feel that it's easy to be generalized to the complex data case. So next, I will talk about how to use this two-sample test to detect change point. So basically, the same thing that we do this for each time. So we begin from time 1, that only this one is observed before time 1, and all the others are after time 1. And we look at the number of edges that connecting between these two groups. So these are these two edges. And then we continue to time 2. Now these two observations observed before time 2, and we can count that there are 1, 2, 3, 4, 5 edges that connecting between these two groups. And then we continue to do this for every time. And remember that time 25 is the true change point. And we see that there are only 1, 2, 3, 4, 5, 6, 7 edges connecting between these two groups. So this is relatively small in terms of that, because now both groups have 25 observations. And we continue to do this for every time. And this is what we get. So here, the x-axis is time, and the y-axis is the raw count that we just see how they are obtained in the previous slide. So at the true change point, time 25, this raw count indeed is relatively small. But this raw count is also small at the two ends. That is because at the two ends, one of the group has very small number of observations. So for example, at time 1, there is only one observation in one group. So we would expect that that observation connect to quite few number of edges to other observations. So we need to standardize this raw count so that they are comparable across the time. And the standardization is the regular one that by its mean and variance. I just want to point one thing here that I put a negative sign here. This is just that I just want to look at peaks rather than valleys, because otherwise, if we just do this standardization, we would expect the change point, we will see a relatively small number. But I just want to look at peaks, so this is flip the sign. And also, the statistic is non-parametric, so the expectation and variance are calculated based on permutation norm. That is, if the norm is true that there is no change point, and if we permute the order of the observation, then we'd expect that it has the same distribution. So basically, we do this permutation, and we get the permutation, the distribution of this raw count under permutation, and we calculate the expectation and variance. And it turns out that we can express that analytically, and they're exact. The expectation of the raw count is very simple. It only depends on the time t, the number of observation n, and one quantity of the graph. So I use G to denote the graph. Also the number of the set of, so I also use G to denote the set of edges in the graph. So the size of G is just the number of edges in the graph. And for the variance is a little bit more complicated. It depends on T and the number of edges in the graph and another quantity of the graph, this one. So GI, so if so for example, it's just some graph. And GI, for example, this is node I, and the GI is a subgraph that connects to node I. So GI is just this graph. So then the size of GI is the degree of node I. So this quantity is sum of square of degrees. And as long as we construct graph, these two quantities are very easy to get. So for example, in this illustration example, that the number of edges in the graph is 49, and the sum of square of edges is 218. So basically, as long as we construct a graph, then we get all these statistics very quickly. And this is a standardized count. So we've already seen this, that this is a raw count, and this is standardized count. And we see a peak here. And we see a peak because I just flipped a sign. So we can see clearly that at the true change point, the standardized count is fairly large. And as a contrast, this is a typical result of a simulation with no change point. And still, this is a raw count, and this is standardized count. and we see that it's very random, and also the scale is different. So here, the maximum is around 1, and if we compare to the previous one, the maximum is around 5. So we can see this very clearly. So the test statistic is just the maximum over the standardized count, CT. And this maximum is over T0 to T1. And there are some pre-specified values. Usually, I will say that 20 will be enough for these two ends. So basically, we cannot detect change point to the very end because we need some observations to kind of like define the region of the distribution in this sample space. And we reject the null if this statistic is greater than some threshold B. So the next question becomes how to determine this threshold. And of course, we can just do permutation, that we permute the order of the observations, and then we will get the permutation distribution of this Cmax, and then we can determine this B. But it's clear that doing permutation is very time consuming, especially when the length of a sequence is long. So we would like to determine this threshold analytically. Now here is the second part, like how to determine this B analytically. So basically, if we can calculate this probability, this is just the p-value. Analytically, then we can determine that B analytically. And this is actually the tail probability of this process CT. And we can also view this to be the summary-wise error rate of T1 minus T0 hypothesis tests. And all of these tests are dependent because they are based on this same sequence. And of course, this CT already have very complicated distribution. So it is impossible to determine the exact analytical formula for this probability for finite t. So we begin with the infinite case that we assume that n goes to infinity. And here is a theorem I prove. So basically, under these two conditions of graph, then this rescaled process converges to Gaussian process with mean zero and the covariance function like this. So I will not talk about in detail of this proof, but I just want to mention a little bit about these two conditions. So the first condition is kind of restrain how density the graph can be. So the densest graph we can get will be n squared. And this is saying that the graph cannot be denser than n to the power 1.105. Of course, these are sufficient conditions. They are not necessary, but I feel like they give some guidelines. And the second one constraint about the hub of the graph. So a hub is in the graph is that a node that has high degree. And here, A, and B are defined as follows. So let's say, let me make this graph a little bit larger. So let's say this is E. This is E is an edge in the graph, and AE is the set of edges that connect to this edge. So it will include the original one, this one, this one, this one, this one, and this one. So this is AE. And BE is every edge that connect to AE. So in this case, it will be all of these ones and adding this one, this one, this one, this one, this one. So this is BE. So the second condition is saying that the graph cannot have a big hub or a bunch of small hubs. So that's what the second one says. And under these conditions, then we can express the probability by this analytic form. So the main term here is b phi b. So also b needs to be of order square root of n so that we can go through every step. Phi b is just the density of standard normal. And the effect of the graph comes in here, this k0 and k1, and they are defined like this. So under the conditions, the condition does not ensure that k0 or k1 to be infinity, to be finite, and actually they can be infinity, and it will not cause any problem if they are infinity. And this h function is the one-sided derivative of the autocorrelation function of this ZT process. And it can be simplified to be this form, and the effect of graph comes in here. And this new function accounts for the boundary overshooting problem because this process is discrete. So I just want to make a small comparison here, that if we look at this, it is actually very similar to the result if we were working on the problem of detecting change point for a sequence of univariate Gaussian distributions with early mean change, and we use the likelihood ratio statistic, and we would get a p-value approximation very similar to this one, but the place for this h function would become this expression, and then so we will see that this result is very similar, that if we just working on the most simple case, that for a sequence of univariate Gaussian observations, and we test whether there is a mean change, and we just use the likelihood ratio statistic, and then the p-value approximation will be just the same one, but with each function like this. And in our case, if we look closer here, so there is something I find interesting. So it's just a few steps. Oops. I think I would like to keep them here. So this is something we can see very easily, because in the left-hand side, each edge is counted twice because it will connect two nodes. So this summation will equals to 2 of the total number of edges in the graph. So then, and also easily by the Cauchy-Schwarz, we know that this will be greater than the summation of n square, and which is just 4 times the number of edges in graph square. So this is equivalent in that k1 minus 4k0 is always non-negative. So we should put h to be always in this interval. And I feel this result is quite interesting. And so everything seems to be quite good at this moment, but we want something more. So basically, the previous result was asymptotic result, and if we want to detect change point that is close to the two ends, then so there are two problems. One is that if it's too close to the end, then the asymptotic will not work. And also, if it's not that close, but already close to the end, then if the number of observation n is not large enough, then asymptotic will not be enough. And also, we see that there is some assumption on the graph for that approximation to work. And we want to apply this to more general graph. And let's see some case. So for example, this is a plot. So under these situations, then the skewness CT is not negligible. So this is the plot of the skewness of CT. So the x-axis is t, and this is just a skewness. And this is on a simulation data with 1,000 observations. And each observation is multivariate Gaussian with dimension 100. And the minimum spanning tree was used in this example. And we see that except for the middle region, that skewness is 0. So here is 0. And all the other regions, the skewness is negative. So which put the previous approximation to overestimate the p-value. And I forgot to mention that, so we can use the minimal spanning tree to be like a graph to connect these points. But we can also use other type of graph as long as it represents the similarity among the observations. So for example, like nearest neighbor graph or minimal distance pairing, that is pair all the, so for example, if there are n observations, it pair them into n/2 pairs, and then the minimal distance pairing is just that pair with the distance minimized. So if we use a minimal distance pairing for this case, we get the skewness of this CT process would be something like this. So then in the middle region, it's okay, but at the two ends, the skewness is positive, which makes the previous p-value approximation to underestimate the probability. So we want to correct for this skewness. And this is the result. So there will be an extra term here that correct for the skewness. I will also not mention about details, but this one has this expression. Here, this gamma t is the skewness of CT. And if gamma t here is 0, then this will make this st to be 1, and then it will come back to the original one. And the one thing I found interesting in that, so gamma t, we can also calculate the exact analytic form, and the expression is very long, but it only depends on these 6 quantities. So the Tn and these 2 quantities we already covered of the graph, and the 2 more quantity of the graph. That is this one, the sum of cubes of the degree, and another one that is the interaction of the nodes that is connected in the graph. So this gamma t, the skewness only depends on these 6 quantities. So this makes it, I feel it's quite a useful approximation, because we can just put this, for example, in R code, just one page of R code, and then we can calculate it out very easily. So we do not need to do permutation. So next, we would like to check whether this approximation works or not. So here is a simulation result. In this case, the number of observations is 1,000, and the table, there's no change point here. And the table showing the critical values at 0.05 level, significance level. And the first column is the result from the first period approximation. I call this asymptotic approximation. And the second column is the one after skewness correction. So I just call it skew. And this one is from 10,000 permutation. And we can kind of think this to be the truth. So we would like to compare the first 2 columns to the last one. And in the first 5 simulations, each observation in the sequence is from this distribution, that multivariate Gaussian distribution with dimension 10. And in these 5 simulations, we just increase the dimension. That dimension here is 100. And these 2 columns kind of try to characterize the graph. And we will see that, so this is the sum of square of degrees, and this is the maximum degree in the graph. And when the dimension is low, and it seems that the graph do not have any like big hubs or whatever, and then it seems that the assumption for the asymptotic work holds, and if we compare these two columns to the last one, see both of them works pretty well. But as we increase the dimension, and then we see that the graph constructed here can have pretty huge hubs. So for example, in this case, the maximum degree is 129 out of, in total, 1,000 observations. So this is a pretty huge hub. And then, so as, the conditions for the asymptotic does not hold. And if we compare this column to this one, it does not work that well. But if we look at this column, the one after skewness correction, it still works pretty well, even under such huge hub situation. And I've checked the results for other type of distributions. So here is Gaussian. I checked other type of distributions such as exponential, and also here the graph is a minimum spanning tree. I also checked for other type of graphs, and in all the cases, the one the approximation after skewness correction works quite well. So it's pretty safe to use this approximation for p-value, for calculating p-value. So now let's look at how the method works in the two application I just mentioned. So we go back to this one. We want to know whether there is a change of author or not. And the data we use is called the word length data. That is, for each chapter, we count the number of words that has length 1, length 2, length 3, and so on. So the data looks like this. So in chapter 1, there are 21 words that has length, that is length 1, 59 is length 2, and so on. And for all the words that is more than 10 characters, they are grouped in this same one. So here each
It's not a very long book, is it?
What?
It's not a very long book. Oh, okay. There are many chapters.
Yeah. there are in total 487 chapters. So actually, there are indeed like some chapters are very short. So, for example, some chapters has words less than 200. So we just discard these chapters. We only look at the 425 chapters with more than 200 words. And so here is just a count data. Each row is a vector of counts. And what we do is, we first standardize the count data to be proportion data, and then we use the L2 norm to see whether they are close or not. So it's just a very simple similarity measure. And here is the result. So the x-axis is the chapter, and the y-axis is the standardized count. And it peaks at chapter 371. So this 320 is the chapter index with the chapter we analyze, because we only use 420 chapters out of 487 chapters in total. So this is the true chapter number at this peak. And the p-value is essentially 0. And so recall that the alternative was there is a change of author in the 3/4 of the book. So the book has in total 487 chapters. So the alternative is seeing that if there is a change of author, it will occur in somewhere between chapter 350 to 400. And we scan over all the chapters and we find something here. So that's a reasonable result. And these two lines are the critical values for the significance level. Here is for 0.05 significance level, and here is for 0.01. And if we look closer, that there are two lines here. One is solid and one is the dashed line. The solid line is from 10,000 permutation, And the dashed line is from the p-value approximation after squeeze correction. So we see that it also works quite well. The p-value approximation also works quite well in the real application. And this is based on the minimum spanning tree. And if we try some other graph, so this is from nearest neighbor graph, and we will see that they pretty give the same result, although they are slightly different, but they basically give the same result. And with this same data, we will know that there shouldn't be any change also in the first 350 chapters. So we like to apply our method to see whether we will find any change point in the first 350 chapters. And here is the result. So indeed, the p-values are all bigger than 0.05. So it seems that there is no significant evidence of showing a change of writing style in the first 350 chapters. And that is what we would like to see. And for the second application, so for this phone call network data, that we would like to see whether there is a change of the phone call pattern along this period. And I tried, so each observation is a network with nodes being these subjects are linked between them if they made a phone call. I tried several ways to measure the similarity of the networks, and they give pretty similar result. And here is the one I feel is reasonable to use. That is, so for two networks, I first count the number of edges that are different between these two networks. And then this difference is normalized by the number of edges in each of the graph, in each of the network. So this is a similarity measure, and I use in the next slide. And here is our result. So its result from, this one is based on the minimum spanning tree, and this one is from the nearest neighbor graph. And they do give a different estimation of the change point. So for this one, it is at time 150, which corresponding to the date December 19th, 2004. And this one is 175, which corresponding to the date January 10th, 2005. So if we look closer, that this is a peak here, and then this will probably be time 175. And here, this is a peak, and this is probably 154. So we see that although they give a different estimation of the change point, there is kind of evidence of showing a change around time here. And also, this is during the winter break. So it's kind of like the phone call pattern changes when they switch from one semester to the other one. So my hypothesis will be that there can either be some there should be some autocorrelation in the data, or this change is gradual, so that the two graphs give a different estimation of the place of the location of the change point. But anyway, it gives some reasonable estimate of the place of the change point. And I will talk a little bit about the power analysis. So here, F0 and F1 can be anything. So we cannot do a complete study of the power analysis. So I'm only looking at the case that observations are multivariate Gaussian, which that we will think that this is most favorable to the parametric method. And if we do have a sequence of multivariate Gaussian distributions, then the first method we will consider is those based on the normal theory. And that's what I would use. And so there are two methods that based on the normal theory. One is based on the Hotelian t-square statistic. So this is the Hotelian t-square statistic at time t, and then we maximum over this statistic to find the change point. And this is the generalized likelihood ratio if we will not know whether the variance would also change. And we also maximum over this statistic. And we will think these are, as to me, these two are the best method for this case, for the multivariate Gaussian case. And here is a result that the length of the sequence is 200, and there is a change at 100, at place 100. And the change in this simulation, the covariance matrix is always the same. The change is a mean shift. And this, so I look at data for different dimensions. So always the length of the sequence is 200, but the dimension of each observation can be different. It's from 1 to 175. And this is just that change in the L2 distance at position 100. And this specific change is chosen so that these tests would have moderate power so that they are comparable. So we can compare them. And the first rule is based on the Hotelian t-square statistic, the maximum over the Hotelian t-square. And the second is the maximum over the generalized likelihood ratio. And the last two is based on graph. And I will tell what's the difference between these two later. But we first look at how the power of this method change. So in this table, the number is the number of trials that out of 100 trials that the method would reject. Reject means that you say that there is a change point at 0.05 level. So the higher, the larger this value, the larger the power of the test. And we see that the generalized likelihood ratio test, its power decrease much faster than the other tests, because we know we would expect this because it estimates a lot of parameters, because for generalized likelihood ratio test, it needs to estimate the covariance matrix for both groups. So this power decreases very quickly compared to the others. And at dimension 10, the graph-based test is already better than the generalized likelihood ratio test in this case. While the one based on the Hotelian t-square is doing pretty good. And we see here at around 125 dimension, this type of graph-based test catches up. And at dimension 175, both this graph-based test is doing better than the Hotelian t-square. And if we continue this, if we continue to increase the number of dimensions in the observation, then the Hotelian t-square will not work if it's larger than 200, because it needs to estimate the covariance matrix. But the graph-based test will still be applicable then. And also based on this trend, we will expect the power of them will be reasonable, because if we look at this difference, it's kind of like the power would kind of depend on the size of the change. It does not decrease as the dimension increases. So I feel it's a good result. And the difference between these two is like this. So one MST is just the minimum spanning tree. And the three minimum spanning tree is something I feel like when we increase the density of graph, the power of the test kind of increase. So this one, so let's define the second minimum spanning tree to be a minimum spanning tree that is orthogonal to the first one. And the third minimum spanning tree to be the minimum spanning tree that is orthogonal to both the first and the second minimum spanning tree. And this three minimum spanning tree is just a union of the first, second, third minimum spanning tree. So this one is denser than this graph. And we see that in all cases that its power is higher. I'm still looking at which is the optimal density of the graph for the test to get the best power, but it's still under investigation. And if at the change point, so still the length of the sequence is 200, and there is a change point at position 100. And if the change is both the mean and the covariance matrix, then we see that the test based on the maximum over the Hotelian t-square, its power decreases very quickly because assumption does not hold for this test. And also, the one based on the generalized likelihood ratio test, it also decreases pretty quickly because of the number of parameters it needs to estimate. And we see here that in this simulation, at dimension 20, then the two graph-based tests outperforms the two based on the normal theory dramatically, I feel. And I think this is also quite common because for real data, it's hard to say that the query matrix does not change. So it's very likely that the method based on tiny t-square would fail because the query matrix may also change. So basically, I finished most of my talk. I think it's just on time. And basically, we propose a new non-parametric method for detecting change point in a sequence of multivariate observation or even more complex type of observations, such as network. And we require an informative similarity measure on this sample space so that we can use this, we can construct a graph on this observation based on that similarity measure. And I think we derive quite accurate approximation for the p-value that we can apply this method very quickly because it's just very quickly to calculate this p-value. And the power of the test is also quite good, I feel. And I think for this test, it will be useful, like if we get a sequence of object data and we know nothing about this data. And but we usually can have some sense of like which observations are similar, which observations are like closer, which observations are less closer. And then we can apply this method to segment this sequence of data into homogeneous segments, and then we can do more detailed modeling later. And of course, there are many other follow-up questions that we need to answer. So the first one, most important one, is that how accurate the estimated change point is, and also like how to extend this to online data, and how to incorporate the autocorrelation along the sequence. We see that like many times the change is gradual rather than abrupt, and how we like to modify this method to deal with these cases. So I think there are many things that need to be done. And thank you very much, and yeah, that's all.
Questions or Tim, why don't you go first, and then
I was wondering, so instead of using the minimal spanning tree, can you use the Delaunay triangulation and count the number of direct neighbours of each point instead of using a minimal spanning tree? That's my first question. And the second question, from a practical point of view, when people write books, is it likely that there is going to be a change point in terms of everything after that is written by one person, everything before that is written before that? Or might it be that actually some chapters in the first 270 were written by other people as well?
So your first question was about like whether we can use other graphs, something like that. So yeah, we can definitely use other graphs. So I think in some result, I also presented the result of another graph, the nearest neighbor graph, that is for each observation it connects to its nearest neighbor. And we can also like construct graph, many ways to construct graph. For example, like for the distance matrix, we can just impose a threshold, and then whatever left in will be like in the graph, something like that. So there are many ways to construct graph. And I haven't looked at all the graphs, but up on the graphs that I've already examined, I feel like they give pretty similar results, although there is some difference. And for the second one, I think like it's very possible that like if the two persons that then the other one may modify whatever the first person write before. The problem here in this case is quite clear because like even for the second author, he claimed that he only write the last quarter of the book. So at least in this application, I think if there is changes, there will be an abrupt change. But I don't know if like for other cases, there may be some other type of change.
So thank you for the talk. I think it's quite neat, your scan statistics. but I think you pay a lot of attention to the form of the scan statistics, but you pay less attention to the form of the similarity measure, which I think is equally important in these problems.
Oh, yeah.
With high dimensions. So your trees are, for example, sensitive to scaling in each particular dimension. So if I rescale, if I attach more importance to those dimensions with no change points, then of course my tree will change and maybe it will fail to detect those change points in the less important dimensions, etc. So I think this is pretty important in all high dimensional problems, however you scan your space.
Yeah, that's
my
very.
first comment, and my second comment is that of course in your examples I could have done that by any other method. It would be good to compare your example from the book writing with some simple Q-sum statistics, etc. And I'm sure Q-sum statistics has a graph interpretation. I'm not sure what it is. I'm trying to think about it, but yeah.
Yeah, I think it's a very good point for the similarity measure. So I think at some point of the talk I mentioned that this is kind of like convert the change point detection problem to the problem of finding a good similarity measure. So so my work, this work was focusing on like from we having the similarity measure, then what we will do in the next, and this part will be taken care of. And for the first part, I feel this is very specific to every application, and there can be a lot can be done in that area. And this work is like not focused on that part. And for the
But the same can be said about Q-sum statistics.
Oh yeah. So I haven't looked at like how the Q-sum statistic would look like in that specific example. So I feel like the point here is that the method is kind of like generic, that it can be applied to many different application areas, while Q-sum statistic can be quite strict to be some applications. And I guess for the first example, I haven't tried the Q-sum, but I guess they may get the same result of like detecting change point at chapter 370 something. I would believe they can also do this, but I think my point here that this method is like more general to other like applications, and this is just like
yes, it is, but there are I think some other methods are also generic.
Yeah.
Can be generic, maybe generic. I don't, but it doesn't matter.
Just to pick up slightly on Piotr's point, you mentioned quite a few different alternative literature. I think one big one that you did miss was ECP by David Matheson and his PhD student. So that's got software in the ECP package on R, and that's a non-parametric multivariate as well, based on rank statistics. So you may want to.
Yes, thank you. I will be very happy to look at that one.
For one of the examples we looked at, the p-value changed as you changed the different types of networks. There's some intuition why the minimal spanning tree would give you more, it was 0.05 something, which is near to being a critical value. So why would the nearest neighbor give you a different result, and what is it picking up?
Yeah, that I was thinking about that problem earlier, and one explanation I think will be that so actually minimal spanning tree has more edges than the nearest neighbor graph because it needs to collect everything, and so that's something like so minimal spanning tree would by nature has higher power than the nearest neighbor graph. So I think that's maybe one explanation.
And a small question. You see, some simulations, you assume that you have normally distributed random variables, 100 dimension. But that means that have you tried with some other distribution? Because then, for me, as soon as you put there normal distribution, either there is a reason why you use it, that's somehow you are losing non-parametrics for me.
You mean like this simulation only look at the normal distribution?
You have there exactly that you have 100 dimension normal distribution that was.
So like, you mean this one or the power comparison one?
Yes, that could be.
The power comparison one? You mean this one?
So that you get, you are generated, multivariate Gaussian distribution. Have you tried for some other?
The problem with other distribution is that it's very hard to find a parametric method in that region. So basically, I'm picking the region that the parametric method would work the best. So like under this case, like our method is still work very good compared to the parametric method. So the problem is like not that we cannot working on like other distributions. It is that for other distributions, it's very hard to get like a very powerful parametric method. And if for example I do not present this, I present some other distribution, and then people may think that it's because the other distribution is very hard to get some good parametric method, and the comparison will not be fair. And in this one, like we know this will be the simpler case for the parametric situation, and this will be the best parametric method we would use. And this comparison, I feel is more fair.
So in your introduction, you mentioned some previous work on kernel change point methods. So it's change point method with RKHS tools. So with these methods, the goal is basically you take a similarity measure on your sample space, and then you build a change point detection algorithm out of it. So how does your framework differ from that one?
You mean which one?
And so just go back to work by the slide with the so these lines of work. So it's basically the first two. So the work by Desaubry and the work by myself.
Oh, thank you. Sorry. So.
But I'm not the only one.
I see. For these two works, so my feeling is that because it's based on kernel, and the kernel method depends highly on the dimension, right? So when the dimension is high, it's highly dependent on like how we choose the kernels.
Yes, sure.
Yeah,
Yes.
so I think that's like the problem.
But then what I don't understand is like how does your method do not depend on the high dimension? Like where can we see in your results that in a way you can handle high dimensions? It's unclear to me.
So basically, it's kind of like one dimension high. It's hard to like impose any like kernel or parametric thing on that one. But yeah, but I feel like we can still define like whether these two observations are close or not. This is an easier problem in my understanding. So, and if we know which observations are close and which are further, and then we can construct like a similarity graph. And then later on, everything is based on that graph.
Yes.
And I feel like that's kind of quite robustic in some sense.
But still, like MSTs are very ill-behaved in high dimensions. So if you take observations in a high-dimensional space and you build a linear spanning tree.
But the MST is built on the similarity measure, isn't it?
Yeah.
Rather than, so it's you take a summary statistic of the similarity measure,
Yes.
that then gives you a one-dimensional observation that you build the minimum spanning tree, or two-dimensional observation.
Yeah, and also like we can use the Euclidean distance by nature, and we can use some other distance.
Yes, but okay. We can take this offline.
Yeah.
There are no more burning questions. It's probably lunchtime, but lots of people seem to be interested in networks. We've talked about it in several different topics. There was a thought of having a informal sort of discussion tomorrow afternoon, because there's nothing scheduled particularly on change points in networks and what the sort of interesting problems might be, and particularly if there are interesting problems that people here might like to work on. Not exactly sure when and where, but we'll try and make it clear by the end of the day. But if people are interested in that, hope they'll come along to that. Otherwise,